Okay, welcome everybody. I'm just going to get things started quickly with just a few housekeeping items and then we'll move on to Adam. So I would like to, on behalf of the library, welcome all of you here tonight. My name is Debbie Krause. Most of you probably know that already, but I feel like for some of you are maybe a little more unfamiliar. I am the community engagement coordinator here, and it is one of my jobs is to organize these types of gatherings, and it's one of my favorite parts of the job, especially since spending the last 2 years not being able to do it at all. It's still kind of exciting to be able to speak in front of people, which I never thought I would say. So I just want to say a couple things as far as the building goes. We are currently open. The library is open till 8 o'clock. So if there are some people that are working around the library, there might be some people coming in to grab a book or do something at the front desk. We've done this many times, and I ask patience for those who are coming in that they have to be a little quieter, and patience for the audience that there might be a little bit of disruption, a little bit of noise happening back there generally when we're checking things out. Bathrooms are just down the hall to your right. There are 3 in a row, and the door locks automatically at 8 o'clock. We probably will be out of here by that time, but if it's going really well, we might not be. You just need to know that if you go out after 8 o'clock, you will not be able to come back in unless somebody stands at the door and waves and triggers the motion sensor. So it's not cold right now, but it might be raining, so you might want to know that just in case you walk outside for a reason. I would like to begin officially by acknowledging that it is Truth and Reconciliation Week. And I'm going to read this because I don't want to mess it up. So for the past several years, we as a library have worked to educate ourselves and others about our Indigenous neighbors, those whose land we as settlers find ourselves on today. As has become customary over the last several years, I have included a land acknowledgement in my welcomes. But as I prepared for tonight and reflected on what this week of Truth and Reconciliation really calls us to, I began to rethink the rote and token-like nature of a land acknowledgement. So instead, I'm going to change things up a bit. So tonight we're here to learn about the only home we have, our Earth. We are going to hear about how it is changing, how we are changing it, and how this will affect us and our children and our grandchildren. Considering this, I invite you to look up. Right above me, there's one over here, and we are sitting under 2 images of the medicine wheel. This iconic circle is divided into 4 separately colored quadrants, the number 4 having great significance in most Indigenous cultures. The colors black, white, red, and yellow that we frequently see in logos on drums and in art signify many different elements in our world. North, east, south, west, air, fire, water, earth, winter, spring, summer, autumn, and many other relationships that we find in nature. In essence, the medicine wheel or sacred circle symbolizes the alignment and continuous interaction of the physical, emotional, mental, and spiritual realities. The circle shape represents the interconnectivity of all aspects of one's being, including the connection with the natural world. And this is what we are learning and discussing tonight. Our relationship with and impact on our natural world. I would also like to invite you to spend some time exploring the Indigenous voices, stories, experiences, and perspectives in our special First Nations, Métis, and Inuit collection. We have quite a few items, and I encourage you to take a look at them. They are in displays around the library or on the shelves, and you can always tell if it's part of that collection by the spine label. It also will have the medicine wheel. So, let me introduce our special guest. Adam and I connected no less than 3 years ago, and due to circumstances beyond our and the world's control, we've had to wait until today to make this happen. But I'm thrilled that it's finally here. Dr. Adam Martin hails from Welland and first became interested in what he calls the science of being outside while earning a bachelor's degree in physical geography at the University of Guelph. He pursued a master's in the forest conservation program at the University of Toronto and followed that up with a PhD in 2012. Adam teaches in the Centre for Critical Development Studies in Toronto. His research focuses on the functional traits of leaves and how the interaction between crops can lead to resilience, taking him across Central America, the Caribbean, and Southeast Asia. Through his research focusing primarily on coffee agrosystems, he and his collaborators have been able to discover the benefits of diversifying agricultural systems. Planting different species and varieties with different genetic makeups in a single system, they found can aid in resistance and the ability to rebound from climate shocks. Adam, his wife, Dana, and 2 children moved to Niagara-on-the-Lake in 2019. Many of you probably know him as a guest speaker on various local Jane's Walks, or maybe you've seen him working hard here at the library. That's where I've met him, usually in that corner over there. In any case, he's sure to become a familiar sight to all of us, and I'm so happy to have you share with us tonight. Finally, Adam.
Thank you very much. How's it going tonight?
Good.
Very good. Yeah, where to begin, because we did try and kick all this stuff off basically in, I think it was January of 2020, just effectively months before COVID happened. Yeah, Debbie, well, first of all, Debbie, thank you for organizing. Part of the motivation for this is when we first moved here, I was always working out of that corner, hiding from my kids while my wife was home on mat leave. So it just seemed like a logical thing to try and do something at the library as well. And before we get started, I want to acknowledge my wife in absentia here. While I get to do fun stuff like this, she's at home taking care of the kids, which is the real hard work of all of this stuff. So good vibes. So my name's Adam. I'm an assistant prof at the University of Toronto in Scarborough. The research that we do broadly focuses on environmental change in forests and agricultural systems as well. But today what I'm going to talk about is a theme that very much underpins a lot of the stuff we do for research and teaching, which is climate change and the causes of it. Debbie, I don't know if she alluded to this, but if you're aware, today is the first of a 3-parter that we envisioned, with each 3 touching on a broad theme associated with how the world is changing around us. And where we thought the best place to start would be sort of in sequence 2 parts related to climate change. The first, which is today, what's causing climate change, and then next month we're going to follow up with that theme and talk about what the future climate's going to look like. Today's discussion is a little bit more on like a global scale of things, and next month we have more information about what probably the Niagara region is going to look like, and prospectively Niagara-on-the-Lake as climate change continues to unfold. So I think the reason why we started with climate change is because it's probably the one environmental theme that's in the news consistently. I feel like it's kind of overtaken all of these other pressing environmental issues. And so I'm going to start with a question. Has anyone over the summer or even recently seen a climate change story pop up in the news? You can just describe it broadly speaking. Yeah, sure.
Oh, sorry, yes, I've seen that.
Oh, yeah, sure. Do you have one specific in mind?
Oh, okay. So Sydney, in Australia, flooding.
Flooding?
Yeah,
There you go.
flooding. They've never had it. They were evacuating the city.
Interesting. I didn't even know that. I mean, there's so many
My
stories.
friend
So
is
Sydney,
there.
Australia is underwater.
Sydney, Australia was underwater, yeah.
There you go. Anybody? Yeah. please.
Danube River at an all-time low.
Danube River is at an all-time low, where oddly last year was at all-time highs. Fantastic example. Anyway, yeah.
Lake Mead? Similarly, the Po River in Italy.
What's that, sorry?
The Po River in Italy?
Oh, another flooding? Okay.
No, drought.
Oh, drought.
Very
Drought.
dry.
There you go.
The Rhine too, because it had to lower the cargo, take offload the cargo off the boats. So
Right.
It's so low that they can go up.
So that's the low water levels that are
Yeah.
happening. And did you have one as well?
Lake Mead.
Lake Mead, oh yeah, that's one I'm a little more familiar with. It's drying to the level that it's exposing all these nasty, toxic minerals and metals at the bottom of it. Yeah, please.
Historic droughts in California and historic wildfires in Europe.
Yeah, wildfires, droughts. Yeah, the California one I'll show in a second. That's the one that certainly I feel like it dominated the headlines in North America, for sure. Yeah, please.
On the other extreme of that, they're expecting 25 inches of rain in Florida.
There you go. So these are all tremendous examples. It doesn't take much to come up with stories that you probably weren't even aware of because there's so many of them. It's almost hard to kind of like keep up with the climate change related news, be they droughts, floods, heat waves, wildfires, whatever the case. And these are just some that I came across. Somebody alluded to there, historic heat waves that were racing through California. They kind of broke at the end of August. It looks like they're coming back. The first wave was broken because a hurricane formed in the Pacific Ocean, which is totally bizarre. This was a couple weeks ago. A lot of the students in the class that I'm teaching have family members back in Pakistan. There's tremendous flooding there. There you go, the Pakistan Prime Minister saying the whole country looks like a sea. These are some, on this point about there's a bunch that you probably haven't even heard of. I didn't really know about this, but apparently there's this monster drought in Spain that's taken a real hit at the world's olive production. And olive oil might be the next sort of food commodity that shows up with climate price shocks in the next little while. This is from last summer here in Western Canada, where we have the worst drought that farmers have ever witnessed. And actually there's empirical data to back that up. And a little more closer to home in the viticulture wine world, climate shocks, particularly associated with really unusual deep freeze events in January and February that, if you've come across this before, look to have probably reduced yield by about 50%. And all of these examples, as well as the one that you've all graciously contributed, are examples of the climate changing and climate patterns showing really unusual types of things. So what we're going to talk about today is what's causing those things. I think that's sort of the first place to start in understanding, I guess, the science of climate change as it's unfolding in real time. So this is what we're going to talk about today. I got 5 things that we're going to knock off in sequence. Each of them are only about, say, 5, possibly 10 minutes at the most. And by the end of it, this is kind of the biggie here. We're going to get to this answer of what the data shows us, what the scientific evidence shows us, what's causing climate change. That's our ultimate goal for today. There's a couple graphs along the way. They're pretty, not simple graphs, they're necessary, let's say, a necessary evil. It's a little bit tricky to talk about climate change and the science of it without interjecting a little bit about that data visualization part that's so critical. But we'll definitely walk through those. So as we go through these 5 points, please interject with any questions that you have along the way. So the first one we're going to start with is this important part about 2 really key definitions in climate change. Forgive me if they seem simple, but they're crucial to lay out. And that is the difference between weather versus climate. Confusion around these two invariably muddles up discussions about climate change. So I just want to get this one out of the way. When we talk about weather, what we're talking about is like what just happened 5 minutes ago, a big rainstorm. The conditions in the atmosphere over a very short period of time. Hours, minutes, whatever the case. Really short-term events, kind of looking outside and seeing what it's like up there. So this would be daily temperature, precipitation, wind, humidity, chill, fog, UV, all of the stuff you kind of check online before you walk out the door in the morning. And what I'm really saying here is weather is short-term in that there's no historical context around it. It's just what you're experiencing at that point in time when you walk outside. So this kind of becomes a little bit tricky because you see things like this. This was from last summer, talking about a Niagara heat wave. The Niagara heat wave that happened last August is in and of itself just a weather event. In the absence of any longer term weather information, it's just an individual event in and of itself, but it's part of a longer term climate trajectory. So, kind of similar, everybody remember the blizzard? Yeah, it was wild, like shoveling for 2 days. Kind of the same deal. This feels very extreme. It feels like a very unusual, I'm always inclined to say, like, this is a weird climatic event, but it's just weather. It's in and of itself a short-term event that without any other information is just one thing unto itself. Climate is a little bit different. When we talk about climate and climate change, what we're talking about is how the atmosphere is expected to behave over longer periods of time. Like how we can expect the climate to look in Niagara-on-the-Lake month over month, year over year, that kind of thing. In particular, anything short of years is really more in the world of weather, whereas we're talking about years, decades, centuries even, we're talking about climate patterns. So there's a much more longer-term historical element of climate. And here we're talking about long-term temperature, precipitation. If you're in the hurricane-stricken parts of the world, how many storms you get, the frequency of storms, the duration, those kinds of things. Long-term records. And so this is our graph number 1, and we'll just walk through this one. This is how you would describe climate in a graphical form. What we're looking at here is on the y-axis, the average long-term temperature in Niagara-on-the-Lake. And if you can see that there's one dot for each month of the year going from January to December. And of course, it's coldest in January, February, and March, warms up during the summer, and then starts to plunge back down just about now in October. So climate, I always kind of like to think of it as like, if you're moving to Niagara-on-the-Lake from Europe or something, it's like, what can you expect August to look like? And based on climate records, you can get a pretty good prediction. You'd have a much more difficult time saying, what's the weather going to look like on Tuesday, the day after I move? Yeah, please.
Yes, you talk about records. When will records start to be kept?
That's a fantastic question. It kind of depends what climate thing you're looking at. Precipitation records are a little more recent. My understanding is the really good precipitation records probably start maybe in the 40s and 50s would be my guess. Temperature goes back a little further. We have pretty good actual observations of temperature that probably go back to like the late 1800s. So those are the things we're observing. Then I'll talk about it a bit. We can use funky things like ice cores and tree rings to try and figure out what the records were way, way long ago, like hundreds of years ago. Yeah, so it kind of depends, but that's what I would say. I would say the stuff we've measured best directly is temperature, and that probably goes back to the late 1800s. Yeah. Just in the interest of time, climate, there's the temperature part. We can also talk about precipitation. For today, we're going to really focus on temperature, so I'm going to just go stick to that for now. Okay, so then by extension, when we're talking about climate change, this is what we're talking about. Any alterations to the way that we think the atmosphere is going to behave over the long term. So we can think about this also like in terms of, climate change in a way is thinking like the predictability of the climate is going down. It's becoming less and less predictable because it's starting to deviate from the historical trends. Okay, I don't mean to make this political, but this tweet just encapsulates this so brilliantly. These two things of weather versus climate get conflated and muddled up all the time, especially, as we'll see in a second, as the climate change debate unfolded. This was before his presidency, but this was a tweet in January of 2014 in response to a cold snap through New York in the northeastern United States. And you kind of see here, NBC News just called it the Great Freeze, the coldest weather in years. Is our country still spending money on the global warming or alternatively climate change hoax? So right off the bat, these are just fundamentally different things. A cold snap is not telling you anything about climate or climate change. I'm sure there's more of those. Yeah. This is the other one. I was trying to think. I was talking with my wife about it, and she was asking, where does Hurricane Fiona stand in all of this, which just hit the eastern part of Canada. And I was looking online, I was thinking, well, okay, where's it at? And, you know, Hurricane Fiona, I don't know if you've seen this. Has anybody been here before?
Yeah.
Okay, I've never been there before. I mean, it's absolutely beautiful. But Teacup Rock is gone, along with a number of other natural heritage sites by Fiona. So this kind of thing, and just the experience that we're seeing people work through after Fiona would kind of make you think, whoa, this was something very, very unusual, very severe, very representative of climate change. But I would argue at this particular moment in time, we're not quite sure. We're not quite sure if Fiona was in fact more intense than all of the other storms that have hit that part of Canada, or if this type of storm is going to come more frequently. We're just kind of not there yet. So the reality, I would argue, we might learn more about what Fiona tells us these storms are going to look like. But right now, I think it's an individual weather event that's part of the longer term storm cycles off eastern Canada. Okay, so that was the first part. So here we're talking about climate and climate change, those long-term things. So I just want to focus on this part really briefly because this is where today's discussion kind of falls in, is how confused the climate science kind of got over the last 20 years or so. Has anyone heard of the climate change debate? Just quick, Kira, you've most certainly heard, yeah, as well. And what's your general understanding of the climate change debate then? Or Kira, if you don't mind offering up.
Oh, sure. I mean, it's
Sorry, please.
not really a debate in kind of the way that I've studied it, but the portrayal of both sides is kind of equal arguments.
Right.
Science versus other evidence.
You hit the nail on the head. For about 20 years, especially through media outlets, we were saying the science is undecided. There's a bunch of scientists saying climate change isn't happening. There's the same amount of climate scientists saying it is happening. And it's this scientific debate. This posed real problems for climate action. And so if you were to flip through like CBC, this is from 2010, but especially through the 2000s, probably would have heard climate change being discussed like this, that there's a debate raging about it. And you would have also seen another extension of that debate, which I'll show in a second. There's like whether or not climate change is happening, but then this other part, which is whether or not humans are causing it. And that was the second iteration of the climate change debate. So this is wild. I don't know who did this. Oh, there you go, Friends of Science. I don't know what that means. Where you get things that say this. You know, the sun is the main driver of climate change, not you, not CO2. I guarantee you this was somehow funded through, fossil fuel interests. No doubt about it. I'm going to come back to this point in a bit. As Kira noted, in the scientific world, this history of the climate change debate is like a whole field of study now in the social sciences documenting what happened. I'll just point to this and then I'll show you some. I think the climate change debate kind of went through 4 iterations. The first, as we mentioned, was this debate, is climate change occurring? I think that one's settled. I'll show you in a second why. The second iteration, very deliberately, was whether or not are humans causing it. I'll show you in a second. The science is very settled in this. The third iteration came up as this question of certain interest groups saying, well, climate change is happening. Sure, people are causing it, but it's too expensive. You can't even conceptualize how economically difficult it's going to be to deal with. And then here, I think finally after a long period of debate, we've turned the corner and now we're talking about what we can actually do to mitigate or minimize climate effects. I'll come back through these. There's like science relating to all of these. I actually came across this, which I think illustrates these points and this progression kind of nicely in sort of survey data. This was on CNN 2017, so recent enough. It was this sort of survey talking about the confusion of climate science through the United States. I haven't been able to find a Canadian version, so let's just go with our neighbors to the north. They asked a number of individuals across the US 5 different questions. And those different questions, I think, almost give a sequence of this climate change debate. So the first one, these maps are all going to look the same. They're the United States broken up into voting districts. And the color of each district is going to range from light blue to dark purpley red, depending on how many people answered yes to that question. So if 0% of people answered yes, it's going to be bluish. And if everybody answered yes to that question, it's going to be purplish. And the first question is climate change real? And you can kind of see, even in places like where you think maybe more than half the people would be like, I don't know, climate change still isn't happening, like in Texas. There's this, as recently as 2017, this emerging consensus actually across the United States that, yeah, climate change is happening. And that's why I'm saying that first step of the debate seems to be over, even in public circles. Things get a little more confusing after that. This is question number 2. Are humans causing the Earth to warm up? And so whereas a vast majority are saying, yeah, it's happening, this is where the uncertainty starts to sort of creep into the picture. And this has real sort of, consequences for how we deal with climate change. So are humans causing the Earth to warm? Now we're starting to get into almost a 50-50 territory, where about half of the population is like, yeah, humans are doing it. And the other half is saying, actually, it's natural causes. We'll talk about that. Hold that thought for a second. There's other elements of this. One thing that's been very effective in this climate change debate is putting this idea that scientists disagree on the science of climate change. And that's very much reflected in this map, which is asking, do scientists agree on these first 2 points? Is climate change happening? What's causing it? And then you're starting to see even more people, 25% maybe on average, oh no, there's still scientific uncertainty, primarily around what's causing it. This one, some of these are peculiar. There's 2 more. This is the next question in the survey. Is climate change bad? I don't know what to make of this. I guess there's a lot of people who are inclined to think that climate change can pose some benefits to society and humanity. I don't know what those would be. I can think of some sort of phony arguments for it, but that's an idea, that climate change is actually going to be good. I very much disagree with that. And then this is one I think is kind of fascinating and a glimpse into people's thoughts. Are there smart ways to fix global warming? And yet this is really quite astonishing that the highest number of people agreeing with this for any survey question is sort of reflecting their optimism that we're going to be able to find some kind of cost-effective solution. I think we can all agree we hope so, but that's sort of the different stages of the debate. Okay. So that's where the research and the stuff we're going to talk about today is kind of centered in climate change, not weather, and this sort of evolved understanding of climate science, where most people agree that climate change is happening. There's still this looming doubt about what's causing it. And for some reason, everybody's optimistic that we're going to fix it. Okay, so these are the kind of sciencey parts we're going to talk about today then, is dissecting a couple of those maps. And the first part we're going to talk about is what controls Earth's climate in very simple, broad strokes terms. This is usually the world of atmospheric physics and atmospheric chemistry, which is definitely not my thing. So we'll just sort of talk about it in general terms. When we think about what's controlling the climate and how temperatures change depending where you are, how precipitation cycles, how the atmosphere sort of flows around, there's effectively 2 primary points that control those things. The first one is the amount of solar energy that reaches the Earth, or the amount of incoming solar radiation that smashes into the Earth coming from the sun. That's really the driving force for all the climate systems that you see globally. Now, this definitely changes depending on where you are in the world, and it definitely depends on the time of year. So, because of those things, as incoming solar radiation changes depending where you are and through the year, that's why you get things like pronounced seasonality, like we're kind of seeing now, right? We were just talking how like the leaves are changing, and that's really reflective of the incoming solar radiation that's sort of smashing into the Niagara region, declining as the seasons change. So this thing, while we can think of that as a localized, you're going to get a sunburn today, as a unit, if you like, the whole planet generally receives the same amount of incoming solar radiation year over year, century over century, I guess millennia over millennia, let's say. That usually doesn't change because it's kind of hard to knock the Earth off of its orbit or, move the sun around, let's say. That number doesn't change. We get the same amount of radiation coming in. There's one way it changes. It can change, so it's very stable over time across the whole world. It can vary over what we call geological timescales. So the amount of solar radiation hitting the Earth from the sun can actually change, but those changes take like thousands, hundreds of thousands, in some cases, possibly, let's stop at 100,000. That seems bombastic enough. It can change over really, really long periods of time. This is something called, I don't know if anybody's heard of this before, Milankovitch cycles. Anybody heard of a Milankovitch cycle before? Oh, yeah.
Years and years
Hey,
ago. I couldn't
sweet.
even find it now. But
Hey, fantastic. Yeah, cool. Yeah, there's something called Milankovitch cycles that actually change this. I'll show you why really quickly, just a really quick graph. Because as the Earth is orbiting around the sun, in our lifetimes, we're never going to experience a detectable change in what that orbit looks like. But over thousands of years, it actually changes quite a bit. Physicists are really good at being able to measure this and predict it and actually sort of backcast it. It can change for a couple of reasons. One, over thousands of years, tens of thousands of years, the Earth can kind of start to wobble. Like it's spinning on its axis. It's kind of like, if you spin a quarter or a coin on a table, and as it starts to lose momentum, it'll start to flop down. It's kind of like the Earth does that, but instead of flopping down, it bounces back up. So it kind of goes boom, 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 back and forth. That can influence how much light, incoming radiation hits the Earth. The tilt, the axis can kind of change a little bit. Right now we're on a 22.3 degree tilt, doesn't matter, but it can kind of spring back and forth a little bit. It can drift. Usually if you see like doomsday conspiracy theory things about why the Earth is going to melt or turn into a hothouse, that's usually why, some change in the axis. But this is, again, a thing that changes over thousands of years, hundreds of years. And the last one is what we call eccentricity, and that is the actual orbit around the sun can kind of become like more circular or more oblong. It can kind of bend and stretch, if you like, over really long periods of time. So for natural reasons, the thing that incoming radiation, the thing that drives Earth's climate can change, but this takes really, really, really long periods of time. These are some of the reasons why throughout Earth's 4.6 billion year history, we've had, and we know we've had, things like ice ages. Because we see climate fluctuations that unfold over tens of thousands of years because of these funky Milankovitch cycles and other factors, but that's a big one. So this is also why, by extension, why we know we see things like fossilized tropical forests found in like Arctic Norway, is because thousands of years ago, we know that the relationship between different parts of the world and the sun was kind of moving around. So this, along with a couple other things, is usually what gets clumped in as natural causes of climate change. We'll come back to that in a second. Okay, so we can have the amount of energy coming into the Earth changing through these Milankovitch cycles. The other big control on Earth's climate is the amount of solar energy that bounces back into space. So the Earth gets smashed by a lot of light, and much of that is actually reflected back into space. Now, this number can change as well, but unlike the Milankovitch cycle, this number, and I'll show it in a second, can change very fast for two main reasons, both of which are related to human activities or human impacts on the environment. The first one, the first thing that humans can do to change that amount of energy that goes blasting back into space is change the reflectivity of the Earth's surface, or what we call albedo. So that's basically the tendency of different parts of the world to send radiation back into space. One example, probably close to home, is snow and ice have a very high albedo. That's why if you walk out on a sunny day when it's snowy, your eyes kind of, it's almost worse than a summer day that's sunny outside. It's because that reflectivity of snow is very, very high. And that's actually what's happening. Large parts of the world, especially those that were previously under snow ice or glaciers are really good at sending that solar energy back into space. But as glaciers melt, they generally reveal one of two things, soil or water. By comparison, both of those are less good at sending energy back into space. Instead, they kind of absorb it like a sponge and start to warm up. This is kind of why, you see, I can't wrap my head around this. This is so bizarre. Sometimes you'll actually see some active environmental management, especially like in the Swiss Alps, where they're trying to prevent glaciers from melting. This was from about 10 years ago, but I think it's still going on now. What they've actually tried to do is drape glaciers in highly reflective surfaces to try and send that radiation back into space. I can't, for the life of me, imagine this is sustainable in any sense of the term. However, there's some sort of humans manipulating that reflectivity or albedo to try and curb climate change impacts. So that's one of them. And then this is the other big one, of course, which may be a little bit more familiar. The short-term changes, or the amount of energy that hits the Earth and goes back into space, can also change really quickly, depending on how good our atmosphere is at trapping that energy down below it and not letting it go out into space. This is kind of the world of atmospheric chemistry, or alternatively, greenhouse gas concentrations. The more greenhouse gases we have in the environment, the less readily radiation can bounce back into space. So instead of going off and not warming our planet, it kind of stays stuck in the atmosphere and starts to warm up over time. So these two things, unlike those Milankovitch cycles, these can change very fast and have been changing very fast. These two things can change on the order of, you can clear cut a forest in a day and change the albedo. You make greenhouse gases, days, months, years, very short periods of time. Let me talk about this one just quickly. I alluded to that albedo. The world is becoming kind of more absorptive in a lot of places. Greenhouse gas concentrations as a cause of climate change is probably the thing that's a bit more familiar and off the top of the head. This is where we're at, just so you know. This came from 2015. In the year 2015, the world broke this very dubious mark of greenhouse gas concentrations. And that is, we punched through 400 parts per million. In of itself, maybe that isn't a big deal, but this is kind of the benchmark. So what would that be? 7 years ago, that's where we hit for the first time, 400 parts per million. That's a measure of greenhouse gas, how concentrated it is up there. I don't know if anyone's on Twitter. Earth's atmospheric CO2 concentrations have their own Twitter account. And this is actually updated, I think it's basically monthly. So whereas 2015, we got over that 400 mark for the first time, this is where we were at in August of 2022. We hit 400, just shy of 420 parts per million. So it's going up fast, fast, fast. I'll talk more about this in the next of the 3 lecture series. Just to put it in perspective though, there you go. This is also from 2018. Carbon dioxide levels in Earth's atmosphere have reached the highest levels in 800,000 years. And to the previous excellent question, which is how long did these records go? Whereas temperature and precipitation, we can maybe get back a couple hundred years, maybe 1,000 years or so. We can estimate past carbon dioxide levels really, really long back by using ice cores, isotopes, rocks, that kind of thing. And so we can make these kinds of scientific claims with a lot of certainty. Just to put, I don't know what's going on 800,000 years ago necessarily, but here you go. Last time CO2 was this high, humans didn't exist. So we're talking about CO2 concentrations that have gone up very fast to record levels that we haven't experienced on Earth in about 800,000 years. Yeah, please.
Is that a worldwide average?
Yeah, excellent point. Yeah, that's a worldwide average. I'll show it again in a second. We're going to talk about global temperature changes. We have a whole bunch of monitoring stations in different parts of the world. So this number here, CO2 Earth, it can definitely vary depending on where you are. But we're talking about, a global average based on sort of a network of monitoring systems. Probably the most famous of these is in Hawaii, which was sort of one of the first long-term CO2 monitoring systems. Mauna Loa, I think. Okay, so just to summarize, this is what we got in terms of what can change Earth's climate. We got long-term mechanisms. That's changes in the amount of energy that actually hit the Earth. That's those Milankovitch cycle things that cause ice ages and stuff. And then we have some short-term mechanisms, which are changes in the amount of energy reflected by the Earth, going back out, albedo, and changes in the amount of energy that gets trapped. And those would be the greenhouse gases. So broadly, as we sort of move to what's causing climate change, these things are kind of broken up into groups: natural causes and man-made causes of climate change, the long and the short term. Okay, so we just got 2 more to go. We'll get to our final question here. This is another graph. We just got to introduce this one because it sets up kind of the final hurrah of the presentation. So I want to come back to this point. How do we diagnose climate change? How do we tell it's actually happening? There's all sorts of ways to do this. As I alluded to before, there's different fields of study that get at this question: hey, is climate change happening? For example, we can extract ice cores and try and figure out how much CO2 is trapped in the bubbles way down there, and try and get an estimate of, okay, if CO2 was this much at the bottom, what did climate look like way back when? We can kind of go back thousands of years. We can use the width of tree rings to try and make some inferences about temperature and precipitation regimes at different years. This is the world of dendrochronology. But what we're going to focus on today, because I think it's the most straightforward, is we can, and humans have, actually set up a network of temperature and precipitation monitoring stations all over the world. It's kind of like super fancy thermometers that are placed very strategically around the world, giving us an idea that over the last 70 years or not, has temperature actually been going up. So we're talking about direct measurements of temperature in different parts of the world. This was from NASA, they give a good rundown. There's all different sort of sources of this. Just to give you some idea, to the previous question, are we talking about a global average? The stuff I'll show in a second, especially at the end, is a global average of temperature change. And the stuff we're looking at is based on more or less, over 30,000 individual temperature and precipitation stations, like all over the world, that have been operating, some longer than others, but let's say 50 to 70 years on average, in some cases longer. So it's a very rich observation. They're starting to be able to do this from space. Every satellite that goes up measures something more and more mind-blowing. And so that's where we're getting into with satellites, sort of real-time observations. But okay, this is the thing I just have to introduce. This sort of when we're looking for evidence of climate change, what does that look like in data? More specifically, what does that look like in a graphical form? So just bear with me on this one. When we're looking for evidence of climate change, particularly as it pertains to increases in temperature, we're looking for something called climate anomalies. That is what it is. Weird climate events. Weird in the context of everything that came before it. And what we're looking for is then difference in present climate conditions or certain climate conditions compared to past trends. I'm just going to pop up one graph that's an example of this, because bear with me, you'll see in a second, I just have to explain this weird scale that we use. So I'm going to show temperature data from the Sahel region in Africa. I don't know why I picked this example. I should pick something better, but it'll serve the purpose. Sort of close to sub-Saharan Africa. Okay, this is the graph, and I'll walk us through it here. This is an example of what temperature anomalies look like in a long-term temperature data set. This is the nuts and bolts of all the climate science that's out there, I would argue. So what we're looking at here are temperature observations, in this case dating back to 1890. So we have some type of actual measured record of that, through to approximately present day. And this is the important part. This y-axis looks a little funky. This is the temperature anomaly, or the weird temperature scale. So let me explain this. You'll notice this big 0 right in the middle. Okay, so these are our temperature fluctuating over time. That 0 corresponds to this green line here. And what that green line is showing you, corresponding to the 0 mark, is the average temperature in the Sahel over the past 130 years. Okay, so if, let's say, let me find an example, 1950 falls smack on the line. That means 1950 was pretty much average. There's nothing weird going on. By extension, any year where these data points fall above, especially like a lot above the green line, anything in here would be a year that's higher than average or positive. I don't want to, that makes me sound like I'm saying that's a good thing. I can't help it. It's a positive temperature anomaly. That means it's above average. So the number goes from 0 and upwards. Now anything below is a lower than average year. So those would be a negative anomaly, if you like, a cooler than average year. So for example, what would that be? 1905 was colder than average. Does that make sense? Is that okay? Okay, cool. I'm going to come back to this graph. This scale. It's critical for the IPCC reports. So that is exactly the kind of information that the Intergovernmental Panel on Climate Change, that's the scientific body that puts all of those 32,000 weather station data together, tries to figure out. Is that globally, over the long term, are we seeing like positive anomalies, negative anomalies, or things just stay the same? This came out in 2021. I always like this question. Has anyone read one of these things before? Here? Yeah, you have this one?
A few chapters.
Yeah, what'd you think?
It's a lot of words.
Oh, they're brutal, yeah.
Substance actionable, like I feel like it's lacking in the translation of information to action.
I couldn't agree more. Kira, what'd you think?
Yeah, I agree. They do have summary documents sometimes, but it's hard to access them.
I had students read, okay, so this thing is, there's sort of 3 different sections. This is the physical science basis, like the nuts and bolts of the science. They publish these summary for policymakers that are designed to inform policymakers. I've had students read them. I think you need to be in grad school to understand what they're actually saying. They're not, anyway, I digress. Anyway, you can find these online. They're all the sources are there. I'm going to show some information that came out in the 2021 climate change report, which was the most recent one. And this is the big graph getting at this question of whether or not we're detecting climate change using, if you see here, that same scale, looking for those weird temperature anomalies within our temperature records. And this is what we got. This data actually, for a number of different sources, we kind of like back forecast it. So bear with me for a second. We actually have some estimates of what temperatures looked like 2,000 years ago. Right up to here, which is present day. 2020 is the most recent number. Here's our green line again. So that's the average. In the climate world, we talk about baselines. That's kind of like the baseline we're comparing it to. And you can see for the most part, yeah, we have some warm years, warm years, warm years. It starts to actually a cooling trend over from about 1,000 years ago, kind of right up basically to the Industrial Revolution. There's this cooling trajectory. And then whammo, if you can see that here, this is our observed trend over the last sort of 100 years or so. So everything squarely is pointing to temperatures in Earth globally showing very pronounced climate anomalies in the positive region. And you can kind of see they're all like bunched up, especially in the last like 20 to 30 years. We're seeing these, this is where you see sort of higher than average temperatures, global temperatures being higher than average. That's kind of the evidence for it. That's exactly what it looks like. Any other sources would show the same thing. I've never seen anything that looks remotely different than that. This is the number that over about the last 150 years, we've seen the global average temperatures go up by about 1.1 degree on average globally. Hold that thought. I'll come back to it because it's a lot worse for different parts of the world depending where you are. So this is the figure. I'm going to deconstruct this one in a second. This is the evidence of climate change that we have based on the best science that's out there. That you can think of it, they get a little wordy to your point. In very recent years, relative to sort of 100 years ago, we've seen about a 1 to 1.1 degree warming that's happening worldwide. That's what that climate anomaly is showing us. This is what I wanted to show you. That's globally, which is a really good question. That's the global average. And I think the global average kind of paints a bit of a rosy picture, quite honestly, because depending where you are, that observed increase can be a heck of a lot worse. Sure, it's kind of averaging at 1.1 degree, but there's parts of the world that are showing a lot higher than that. So what we're looking at here is the world. This comes from an IPCC report as well, colored according to basically that climate anomaly, that funky increase in temperature. Anything in blue, which few and far between, would be places that have cooled over the last, let's say, 20, 30 years, relative to 100 years ago. Any places in red colors would be those that have warmed. So to almost, unless you're hanging out, who would that be, like the North Sea? I don't know, unless you're sailing in the North Sea for some reason, chances are over the last little while you've experienced an increase in temperatures. Other parts of the world, like the Arctic, are especially warming up very, very quickly. On the order of upwards between like 1.7 to 2.5 degrees. And that is a tremendous amount of warming in a short period of time because of those short-term things. Next month, we'll talk about this kind of map in a bit more detail. We have one for Niagara-on-the-Lake showing kind of what it's going to look like in the future. Okay, so the last point that we're going to cover then, so that's what we got for diagnosing climate change, using that funky thing, those temperature trajectories, this idea of above average anomalies. The last point, and then we'll wrap, which is what's causing those then? This is sort of that area of the debate that's been unfolding. Okay, this is a little bit trickier. It's kind of the world, this is the world of climate modeling. Has anyone heard of a climate model before? Okay, broad strokes. Yeah, do you have like a rough definition?
Well,
I don't mean to put you on the spot.
I know, I've heard of it because of the UVic climate models.
Oh, yeah. Yeah, it's a little bit tricky to put your finger on. Sorry, that was a bit of an unfair question. It's a fancy computer program, I think is the best way to put it. And that computer program, it's not like a video game, but it's a ton of equations in that computer program. And those equations describe in math terms how the climate works. And within those models, we have a couple things. We have inputs into the models. Those are things that make the climate work, like greenhouse gas emissions, ocean circulation, all these kind of sophisticated, complicated things that make the climate work. We also have human activity as a big input, greenhouse gas emissions in particular. And then we get a bunch of outputs from the model, which is temperature and precipitation predictions. So you can kind of mess around with these models and basically flip the switches on and off to try and tell us, like, okay, what set of characteristics actually best describe that climate increase that we're seeing in general terms. So let me put this in one last figure, second last one here. This is pretty much the same graph that we just saw a couple seconds ago, where we have temperature anomalies on the y-axis over time from 1850 to present day, kind of zoomed in a little bit. This 0 going across here is our average, that green line that we've seen before. Now, there's 3 jotted, darty curves on this graph. I just want to point out the black one. That's what we've observed. This is, if you can make out the black line in there, it's going like this, and then up here. That's the trajectory of global temperatures that we've actually observed with those climate stations. Now, we can add in a couple of the additional lines from these fancy models. The first one we'll add is here. And what this is, you can read it there, simulated human and natural factors that make the climate change. Now that's this brown line here, and it's going like this. And it's following pretty much the exact observations. So let me unpack that just a little bit. What that's telling us is with our fancy climate models, if in those equations we account for natural processes as well as human activity, like greenhouse gas emissions or changes in albedo, those models can pretty much spit out outputs or predictions that match almost perfectly to what we've actually observed. Like, okay, if we include these human activity and natural processes, we're getting a pretty good match, suggesting that both human and natural causes, well, secondarily human causes, are very important contributors to this black line. They're kind of like following over each other. Did that make sense? Okay. Now, what if you flip off the human switch in the models? That's when you get this blue line down here. If you run the same computer program, but you say, you know what, we're actually going to turn off those human contributions, and we're just going to say the climate's determined by natural processes. Let's see if we can actually replicate what we've observed. It just simply doesn't work. Actually, if you do that, if you flip off the human switch, you get this green line here, appropriately, that's just jogging along, jogging along, jogging along, jogging along. In particular, in this case, solar activity, Milankovitch cycles, and volcanic activity. If you only switch on those natural switches, you actually wouldn't predict at all that the Earth's climate's changing, because these things simply haven't changed enough over this time period to make the temperatures go way up. Instead, it's very much flipping that human switch that makes the models predict what we've actually seen. Okay, so this is the last figure here. So we remember this little bar graph that we talked about. This is what we've observed globally, about a 1 degree increase in temperatures. We can kind of break this bar down into chunks. Okay, so what are the human things that might explain part of this bar? What are the natural things that might explain part of this bar? And that's what this figure does here. This will be the last one for today. Okay, so same deal here. We got climate anomalies. This is basically zero change, or our average temperature. And I just want to, sorry, let me say that again. We have, you kind of can't see them. There's actually 5 bars here. Each of them are components of this bigger one. Okay, so this is the total human influence, greenhouse gases, other human drivers like albedo, solar and volcanic drivers, or internal variability. Let me explain that. Let's focus on these 2 here. These would be natural processes, like solar incoming radiation, the amount of light that's actually blasting into the Earth, and volcanic activity, which sometimes, I guess, can heat up the world, and also internal variability, basically how hot the center of the Earth is. And you can kind of see here, these 2 things, in terms of how much of this they explain, you probably can't see it because it's nothing. These 2 things, these natural processes, for all of the data we have, explain absolutely 0%. Yeah, I'll say 0% of observed climate change. There's no explanatory power, as far as we know, associated with these 2 things. Alternatively, if we dissected this graph, we know that based on how much greenhouse gas has been pumped into the atmosphere, the world should actually be a bit warmer than we've observed. These greenhouse gases have a tremendous influence on making temperatures go up, actually more than we've observed, which sounds weird because there's actually things humans do to the environment to cool the Earth. That's this guy here, other human drivers. Very bizarre, it's very non-intuitive, but sometimes I think the best example is cutting down forests, especially forests that are covered in snow for large parts of the year, like in the boreal. So green foliage absorbs radiation, kind of warms things up a little bit. If you chop those forests down, much more of the boreal landscape is actually reflecting more energy out into space. So ironically, there's actually human things that we do to cool the planet. I don't have it here. There's some totally bonkers ideas that we should like clear cut the boreal to cool the planet off. I don't get behind that idea, clearly, but that's kind of where that comes from. So taken together, these natural things explain none of this graph, and the total human influence matches it effectively perfectly. And that is this combination of greenhouse gas emissions, that's the biggie, and changes in the reflectivity of the Earth. That's sort of the secondary component. So that's where we'll wrap. I'm just going to show this last one here. Actually, sorry, I just have one more after this. This was in Time magazine just about 5 years ago. The climate is changing, but not just because of humans. Here's why that matters. All of these competing, back to this idea of the climate change debate, all of these competing causes of climate change are still swirling around in some muddled ways. And I'll just show you the one quote from this article from Time, which was kind of disappointing. It reads, man is indeed responsible for a large portion, possibly even a majority of global warming, but also in play are complex gravitational interactions, including changes in Earth's orbit, axial tilt, and torque. So that's actually Milankovitch cycles that they're talking about. But the science actually doesn't support this whatsoever. There's no evidence that this is actually the case. The last thing I'll just wrap in, it seems kind of maybe like really commonplace to know that humans are in fact causing climate change. I mean, I've been studying this stuff for what feels like forever now. And many other long before that. It was actually only in the 2007 IPCC report that they actually came out and said, you can read it here, most of the observed increases in temperatures are very likely due to the observed increase in greenhouse gas concentrations. So it was actually only, what would that be, 15 years ago, that the IPCC came out and made this assertive statement, that the evidence was strong enough to say that. So it's an interesting area that it's kind of something we might take for granted now. It has a relatively young history in terms of the science. I'm going to skip over this one and just wrap on this one. There's all the question of where do these greenhouse gases come from? Maybe what activities are actually causing climate change? This is has anyone seen our World in Data before? This website is phenomenal. If you have a question and want to see it visualized, this is your place. These are, when are these from? Year 2016. They haven't really changed much. These are where greenhouse gases are coming from. These are always the two: energy extraction and consumption, and agriculture, forestry, and land use. Those are invariably, and have been for a long time, the two biggest sources of greenhouse gas emissions. And all of those are kind of broken down into subcategories. But when we talk about mitigating climate change, these tend to be the two. So arguments for sustainable agriculture have a really strong climate change component to them. Arguments for sort of decarbonization and the move away from fossil fuels are, of course, clearly embedded within the sources of our greenhouse gas emissions as well. I say, my last point, this kind of reflects probably household usage as well, I think, in large part, but maybe that's a different topic.
It's a very low figure for industry.
Yeah, industry kind of, oh, sorry, go ahead, please.
No, but your industry figure shows 5.2%, right?
Yeah, that's weird. I mean, the lines of these are kind of blurry, right? Like, is this not industry? Is, energy use in buildings not industry? So, yeah. Well, there you go. How does that make sense? This is energy use in industry, but it's lumped under energy use. So it's a little bit messy, of course, but very important. Yeah.
Do you consider a forest fire like a weather event?
Yeah.
Because I don't think they're given enough credibility towards contribution to the cause of climate change. Because to be honest with you, they're a self-perpetuating monster.
Mm-hmm.
That what they do is they're maybe caused by global warming, which is causing droughts, and then these forest fires start. But they're enormous and they're growing. For a decade they've been growing. And they self-perpetuate because what they do is they pump enormous amounts of carbon into the atmosphere, particulate matter, and heat.
Yeah.
And it reflects back to the earth. And then it creates more warming. And they're monsters that self-perpetuate themselves.
Yeah.
And I don't see them ever shown on any of the graphs.
Yeah. It's a wonderful point. A couple points on forest fires. This is a different theme in predicting the future of climate. The big thing we're not sure about are what we call feedback loops. That is climate change making other things worse, and those things then making climate change worse. Forest fires would be a great example.
When we use the forest, we use the carbon sink.
Exactly.
So it's a whole thing that they perpetuate their growth and the size of them and droughts. And in the last decade, the growth curve on the size of the fires has been...
Oh, it's unbelievable.
The proclivity, Australia, South America. As soon as we're in our winter, they're burning. As soon as we're in our summer, we're burning. BC this year was burning like crazy. The weather reports in all the cities in BC were smoke. That was the weather report, smoke. I mean, we're talking about reflecting the heat back to
Yeah.
the earth. And we're just talking about them growing.
You hit the nail on the head. When we talk about next month what the future climate will look like, I'll allude to that, this unpredictability of what we call these feedback loops. Like I said, climate change making something worse, that's something then making climate change worse.
Exactly.
Just the last point on that. Why you tend not to see forests in here is because a lot of this data comes from country level reporting of greenhouse gas emissions. And for a long time, I haven't followed it in a while. I don't know, Kira, if you follow this. Countries could decide to include or to exclude their forests. And it was kind of a really tricky question because in Canada, for example, if we were on the hook for reducing our greenhouse gas emissions and we chose to include our forests, that would mean that all the forests that burn from a forest fire, all the forests that got smoked by like mountain pine beetle, we'd be on the hook for actually paying for those emissions or somehow recouping them. So it's a little bit, these kind of national scale accounting things. Sometimes the devil's in the details. I think you hit an excellent example. Forests is one of them.
It's huge.
Yeah, but you're right. The climate change stories we talked about, it's forest fires. I mean, it's
But
really
everybody looks
astonishing.
at it as it's a result of climate change instead of it being a
Yeah.
cyclical cause also of climate change.
Yeah, these feedback loop ideas. Yeah, please.
The one feedback loop that you might talk about possibly is the melting permafrost.
100%. Ooh, the carbon bomb.
Methane being much worse than carbon dioxide.
I couldn't agree more. I think maybe we'll save that one for next time. The basic idea where forest fires are, climate change makes it worse, that makes climate change worse. The one is melting permafrost in the Arctic. There's so much carbon that's locked up in those frozen soils that once they start to warm up, microbes start to decompose that stuff, and the microbes are respiring, breathing out as they do that. So you'll often hear it as this sort of carbon bomb that's up there. And that's, it's making me shiver. So I heard a colleague talking about like, the expectation is that just the top is going to blow off the permafrost with a big carbon explosion. Probably not that bad, but excellent point. That's a great feedback. Good.
But another loop is snow and ice reflect heat.
Yeah.
And water absorbs it.
Yeah. Oh yeah. That albedo kind of thing. That's almost like the quintessential example that at least I teach in class is like, snow melts, exposes more seawater, and the water warms up. It preferentially sort of sops up.
And then man cutting down the forest too, like clear cuts and so on. I mean, I was a flyer, my paragliding.
Oh yeah.
And you'd always get your thermals over the clear cuts.
Oh
You
really?
could fly forever over the clear cuts.
There
As
you
soon as
go.
went over the forest or water, down you came.
Oh interesting. You
Yeah.
can sort of experience a
So
localized
you'd be
climate change.
feeling the heat coming.
Yeah, Gordon, please.
Well, first of all, thank you so much for
Oh,
a really, really interesting presentation
Thanks.
and made understandable in simple language, which I think we need much more of to educate the general public.
Thanks, Gordon.
One thing which I think is very important are changes in world population. I mean, you've made the case that human activities, particularly the demand for energy, the demand for agriculture, are producing greenhouse gases and therefore inducing climate change. It's really important, I think, that global populations are changing dramatically. I mean, in my lifetime, which is from the early 1940s, at that time, 1940, 2.5 billion people on Earth, and now more than 3 times that. And the projection is that by 2050 there might be another 2 billion people. So the argument is people cause greenhouse gases inducing climate change, the more people there are, despite mitigation attempts, the likelihood is that there will be more human-induced climate change. I don't know whether you'd like to comment a bit on the
Yeah.
demographic changes.
Couldn't
As
agree.
a sort of underpinning, of underpinning importance.
Yeah, I couldn't agree more. I think if we're talking about at its base level, oh please, would you like to?
Well, I'm just following on Gordon's remark here. Do we measure how much heat each human being
Oh.
gives off?
That's a very interesting question.
More than others.
Yeah.
You get 90,000 people at a football game.
Yeah.
There must be an enormous amount of
Yeah.
heat which goes into the atmosphere.
Yeah, it's a very interesting question. I'm sure there's a scientist working on that one. So. Oh yeah,
It's
please.
HVAC, it's 250 meters per person.
Oh, right. Okay. Oh, HVAC. Yeah, there you go.
Well, calculate the size of the air conditioner.
Yeah, interesting. Very interesting.
There, I mean, it's just like exactly.
Yeah, it's very interesting. I would just probably contend that it's a great question. It's very thought-provoking. Probably the scope of Earth's climate system is so monstrous, and these other factors are so overwhelming that the sort of individual radiative heat that you give off probably doesn't actually drive the climate per se. That would be my guess.
They wouldn't drive, I mean, make some very tiny, small countries
It's a very interesting.
to temperature.
Yeah. But Gordon, I want to come back to your point. I think, we're talking about what's causing climate change from the greenhouse gas human perspective. I couldn't agree more. At its basal level, we're talking about the consequences of human population growth that has gone up exponentially. I haven't seen recent predictions, but it's probably on that trajectory still.
It then creates an exponential growth of livestock.
Oh, sure, yeah.
To feed us.
Yeah.
Residential buildings.
Yeah, all of these things sort of
And the
scale.
methane from livestock is enormous.
There's
Yeah,
a model by Hans Rosling, I think, in the Karolinska Institute in Sweden,
Okay.
where he's actually done, he's got a really famous, TED Talk where he actually shows the change in demographics and the breakdown.
Yeah, they're startling. I think some of the demographic slowdown, like there is a demographic slowdown happening in developed parts of the world where reproduction rates are starting to dip below what we call replacement fertility, which is like 2.1 oddly kids per family. It's starting to dip below that. But in the developing parts of the world, in the emerging economies like Brazil, Russia, and China, well, not China, that number, by all accounts, is still going up. Gordon, great point. At its core.
Well, just following up on that, while global population is likely to rise by perhaps 2 billion by mid-century, it's totally unequal.
Yeah.
Because by that time, the population of China will be decreasing.
Right.
And many countries are already decreasing. Russia, Japan, East Europe, they're already markedly going down.
Yeah.
And the
Yeah.
big increases are going to be in sub-Saharan Africa,
Yeah.
where fertility rate is still very, very high,
Yeah.
such that by the end of the century, Nigeria may have more people than China. I mean, that's
Yeah.
debatable, but it's just incredible prediction.
Yeah, there's a role for demography here. I would just wrap on that point with the idea that I think climate science has always tried to wrap its head around about what the most politically savvy way to address climate change is. And probably population growth is a bit more of a tricky one to propose. So, but yeah, your point is well taken.
And this is a terrible time in the climate change venue. It is a terrible time for war.
Yeah,
I mean, it's not doing anything to help.
yeah, we're starting climate conflicts.
Yes.
Please in the back and then Kira.
Yeah, I'm just curious, I think just on one point. 20 years ago, we used to say HVAC 18% of the energy used worldwide. And I'm trying
Yeah.
to track that down. Do you have any idea or seen anything more recent?
I have a corollary, like a secondary point to that, but please, yeah.
Yeah, so around 2019, the amount of electrical energy consumed mining cryptocurrency
Yeah,
was
that's-
equivalent to the consumption of Ireland or Czechoslovakia.
Yeah.
I saw that
Yeah.
number, something like 16 or 18% was before Bitcoin.
Exactly. Now, that's just cryptocurrency mining, not Google.
Yeah, there was yeah, so I don't know the exact answer to your question about what the internet has pumped out. That was the example I was going to say. There's this paper that came out about 5 years ago that put the carbon emissions profile on cryptocurrency mining. I don't understand this stuff whatsoever, but just to cool the servers, it was like a national carbon profile. So yeah, that's the cloud.
One thing you know about the cloud, which sounds nice and fluffy. These are enormous factories.
Yeah.
Huge, bigger than Home Depot,
Mm-hmm.
loaded completely with servers
In-
that take gigawatts, literally megawatts to run them.
Yeah,
And cool them.
the cooling. I was just wondering. Well, it's not in there. Okay, Kira, please.
Well, it's not completely related to that, but it was just a interesting point about which areas of the globe are getting, I guess, larger in population.
Yeah.
They're also some of the hardest hit, and usually the areas that don't have the resources to adapt to climate change.
Yeah.
Or, enact mitigation measures, so it's kind of a very complex struggle to deal with.
Yeah, 100%. Next month, if you're kind enough to join, we'll sort of show the maps about what the future climate's going to look like. Yeah, the predictions for developing parts of the world are especially rough in terms of increases in temperature and changes in precipitation. So to your point, it's usually those parts of the world that are least capable of responding that are actually squarely in the crosshairs of the worst impacts of climate change.
Has a date been chosen for next month?
Yes. Yeah. We're doing it the final Tuesday of October and the final Tuesday of November. So, yeah.
The date in the paper for the October is incorrect.
Oh.
It's the Tuesday. So
Tuesday.
they said the 27th. It's the 25th of October, and then the last Tuesday of November. So yeah, I hope everybody joins us. I feel like this conversation can go on and on, and we can continue it next month.
Yeah. Well, that seems a good place. Debbie, thank you so much for organizing. Everybody, thank you. I really appreciate your time.
Tell others we have more room. I can put more chairs in, but this is a great crowd anyway.
Hey, thank you.
Yeah, great.